Hello students, I am Randhir Kumar. In this video, you are going to learn about Gauss law and its application. Okay, before going to the Gauss law, we will see few topics which are previously taught and it is used in this topic. So electric charge. So you already have read about electric charge. There are two types of electric charge. One is point charge, another is continuous charge. So in point charge, as it suggests, there is a point charged object. So if this is a point charged object and it has a charge value q, so this type of object is known as point charge. Another is continuous charge. So it is usually on the 3D object. Okay, so one of them is linear charge distribution, other is surface charge distribution and volumetric charge distribution. In linear charge distribution, we can see there is a rod and it has a uniform ch- charge. Okay, q. So linear charge density is defined as q by l. L here is length of rod. Similarly, surface charge distribution is like of areal charge distribution. So if there is any conducting sphere, let's assume there is a sphere and it has total charge q. So surface charge density sigma will be q by area. And as you know, the surface area of any sphere is 4 pi r square. Similarly, volumetric charge distribution. So if there is a non-conducting sphere and let's assume it is uniformly charged, so volumetric charge distribution is denoted by rho and it is q by volume, and you know the volume of a sphere is 4 by 3 pi r cube, so it will become 3q by 4 pi r cube. Okay, so in application of Gauss law we are going to use lambda, rho and sigma. So next, electric field lines. You have already taught about electric field lines, and here we discuss some properties which are important for the Gauss law or electric flux. So as you know, electric field lines originate from positive charge and terminate at negative charge. So you know this kind of. Or you can say that in a charge free space, electric field lines are continuous. Okay. Next, we know that electric field lines cannot make closed loop. So electric field lines never make closed loops. Okay, never. And you already have taught that electric field lines indicate the force or electric field. Okay, so this indicates electric field due to charge. Okay, and the relative density of electric field lines uh, tells us about electric field intensity. So its relative density is kind of measure of electric field intensity, and these are vector quantity. Electric field intensity is vector quantity, and electric field lines are imaginary lines. Okay, next. So now we recall the electric flux. Okay, so what is electric flux? So as you already have read about, electric flux is defined as phi, which is equals to E dot S. Okay, and it is a scalar quantity. As you know, this is the dot product. Okay, and as you know, the surface area, this indicates surface area, and as it is a vector quantity, So the direction will be normal to the surface. So in this figure it is indicated by two surfaces. So in surface A you can see that the electric flux is perpendicular to the surface, right? And the surface, the direction of surface is normal to the surface. So the direction between E and delta S, or angle between E and S, surface area and electric field, in this case is 0 degree. Okay. So as you know, if you find the magnitude of flux, it will be E S cos theta. Similarly, in surface B, second diagram, you see that electric fields lines are passing through this surface but at an angle of theta. You see here, this is the angle theta, angle between surface area and electric field. Okay. So let's move to the Gauss law. First, we will see an illustration, then we will state the Gauss law. So first we calculate the flux. So let's assume this is a very small area delta S. So delta phi will be equals to E dot delta S, right? And you can see that this is a perpendicular. The direction is perpendicular to the surface. So there will be theta will be 0. So it will be dot product. So it will be directly, you can say that E delta S, right? Now we integrate it for all surfaces. Okay. So you also know the electric field due to a point charge is Q 4 pi epsilon distance square. Okay. So you put it here, it will become Q 4 pi epsilon r square delta S. And the surface area of any sphere is 4 pi r square. So now for total flux, you integrate it, it means you put the whole area. So it will be Q 4 pi epsilon r square into S. Here you are using full S because we have integrated this. Okay. So integrating this will give you 4 pi r square. Now you can see that 4 pi will be cancelled, r square will be cancelled. So flux will become Q by epsilon. So the Gauss law states that the flux due to a charge enclosed by any Gaussian surface, any surfaces enclosed. Okay. So the flux due to any charges enclosed by Gaussian surface will be equals to Q by epsilon. This is the statement of Gauss law. Okay. So now we will discuss some important points related to Gauss law. So the surface which we are using to enclose, okay, is known as Gaussian surface. Gaussian surface. Okay. And one of the important point is it should not pass through any discrete charge. Okay, any point charge or discrete charge. Point charge. Earlier, we have recapped that what are point charge and what is continuous charge. But it can pass through. It can pass through continuous charge. Continuous charge. Okay. So if there is a charge Q1, Q2, Q3, Q4. Okay. So here you can see that Q1, Q2 are outside the Gaussian surface and Q3, Q4 are inside the Gaussian surface. So the net flux is independent of charge outside the Gaussian surface. So Q net will be equals to Q3 by Q4 divided by epsilon. So one more important point is there will be flux. Okay, there will be flux due to external as well as enclosed charge. Okay, it means through this surface there is also a flux due to q1, q2, q3 and q4, but net flux always depends on q enclosed. So here it is q3 plus q4. Okay, so this is the formula of net flux. Now we can move to the its application. Okay, so first is field due to infinitely long straight uniform charged wire. Okay, so initially I have told you about the continuous charge. So in this you can take lambda, linear charge density. So it will be q by l, right? Now you are taking an imaginary cylinder. Okay, so this is the imaginary cylinder, the dotted line. So what is the charge enclosed by this cylinder? So Q enclosed will be lambda into length. So here let's assume the L is length of cylinder. Okay. Now, and this is the imaginary cylinder. Just to find the electric field due to this long infinitely long straight uniform charged. Okay. Now, what will be the surface area? Okay, what will be the surface area? So as you know, we can take the surface area through which there will be flux. So it is an infinite charged, so we will assume the flux will be like this. So we will only take the curved surface area. So here S will be 2 pi r into L, right? Now you know flux net equals to Q enclosed by epsilon. But you also know this is equals to E dot A, area. Now when you calculate electric field, it will become Q enclosed, which is equals to lambda into L, area which is 2 pi RL into epsilon. So it will be lambda divided by 2 pi epsilon r. So this is the electric field due to infinitely long, straight, uniform charged wire. Okay, let's move to the another application of Gauss law for finding the electric field due to uniform charge infinite plane sheet. So this is the example of infinite plane sheet. So in infinite plane sheet, there is only one layer of charge, okay, because it is a sheet, okay, and it is made up of only charge, okay. So if it is infinite, they have assumed a cuboid, okay. So this is an imaginary cuboid, okay. So there will be electric flux due to surface 1 and surface 2, okay. So what will be the area, net area through which the electric field lines are passing? So area 1 plus area 2. So S will be total. So assume it is A and A. Okay. The dimension of these surfaces. So it will become A square plus A square. Or you can say directly 2A. Okay. A1 plus A2 or A1 equals to A2 equals to A. Okay. The area of this surface. Okay. Now, what will be the net flux? So net flux will be equals to Q enclosed by epsilon. So here it will be sigma into A, which will be Q enclosed, okay, and divided by epsilon. And you know that it will be equals to E into area net. So area net is here 2A, which is equals to sigma A by epsilon. So While calculating it, you can find the electric field is equals to sigma by 2 epsilon. So electric field due to uniform charged infinite plane sheet, it is sigma by 2 epsilon. Let's move to another application to find the field of a uniformly charged infinite conducting plate. So in infinite conducting plate, there is two surface, surface 1 and surface 2. So here the Q enclosed will be 2 times of sigma A. Okay, and like previously, you can find the total area. Total area will be a1 plus a2, which are equal, so we can say 2a. It is similar to the previous one. And finite here will be 2 sigma a by 2a, sorry, by epsilon. Okay, q enclosed by epsilon. Now electric field into area, which is 2a, is equals to 2 sigma a by epsilon. So you can calculate it, and it will be electric field will be sigma by epsilon. So we can say that electric field due to a uniform charged infinite conducting plate is sigma by epsilon. Let's move to the another shape, which is thin spherical cell. Okay. So in thin spherical cell, we are trying to find electric field at two positions. One inside, another is outside. So inside, when you take any Gaussian surface inside the spherical cell, the Q enclosed in this case, Q enclosed is 0. When Q enclosed will be 0, finite will be 0. When finite will be 0, then electric field will be 0, because here surface area will be 2 pi, sorry, 4 pi r square. Okay, whichever r you take from the center. Okay, now for exterior, okay, exterior to the cell, so q enclosed will always be equals to 4 pi capital r square, which is the radius of a spherical cell, into sigma. Correct. Now finite will be equals to 4 pi r square sigma by epsilon, and the area will be at any radius r, it will be 4 pi r square. So electric field will be finite divided by s, which will give 4 pi r square sigma divided by epsilon. Okay, and total area, which is 4 pi r square. So this will be cancelled out. So it will be, let me erase some part. So it will be, electric field will be sigma r square by r square epsilon. And this sigma, we can say that here it is q, total charge on a spherical cell, divided by 4 pi r square. Even if we replace this sigma with this, it will become q by 4 pi epsilon r square. So electric field due to uniformly charged thin spherical cell is Q divided by 4 pi epsilon r square. Let's move to another shape. Electric field due to uniformly charged non-conducting sphere. So draw any Gaussian surface inside and outside. So first we will go for inside. So for inside case, as we know, let's assume the density is rho because it is uniformly charged. Okay. So the Q enclosed will be 4 by 3 pi r cube, which is volume, into density, charge density. Okay, this will be Q enclosed. So phi will be Q enclosed by epsilon, and electric field will be phi by area. And area, this area will be 4 pi r square. So put the value. So it will be 4 by 3 pi r q rho epsilon and 4 pi r square. So solving it, you will get uh, r rho by 3 epsilon. Now for outside the sphere. Let's assume this is outside the sphere and it is a small r. Okay. So Q enclosed will be 4 by 3 pi capital RQ into rho. And flux will be Q enclosed by epsilon. And electric field will be Q by A. And the total area will be this Gaussian surface, which will be 4 pi R square. Now solving it, you will get 4 by 3 pi RQ rho enclosed and area is 4 pi R square. Okay, so it will be r cube rho divided by 3 epsilon r square. Okay, so electric field due to uniformly charged non-conducting sphere, outside will be this one and inside will be this one. Okay, in the next video we will see few questions which are previously asked in JE. Okay, thanks, have a nice day.